Okay, so welcome to this video on the proof of Fermat's theorem. Okay, so I'm just going to state Fermat's theorem so that people who have come here looking for a proof of Fermat's last theorem can leave. Fermat's theorem is that if you have a prime number P, which is congruent to 1 mod 4. Now what does that mean? That means that in modular arithmetic mod 4, that the prime number, if you take the map, the ring homomorphism, which maps the integers onto z mod 4z, it means that your prime is z mod 4z, that your prime is taken onto 1 in this ring here. So it basically means that if you look at the integers, the line of integers, here's 0, here's 4, here's 8, here's 12, that your prime is one of these numbers. It's 1. It's 1 bigger than the multiple of 4, so it's always in this position. So this is 0 in the ring z mod 4z. All of these elements are mapped onto 0 in this ring. These are all mapped onto 1, so 1 is mapped onto 1, 5 is mapped onto 1, 9 is mapped onto 1, 13 is mapped onto 1, and we've already got examples of primes here. So 5 and 13 are both primes, so these are primes which satisfy this. They satisfy this condition up here, that they are congruent to 1 modulo 4. Primes such as 7 do not satisfy this property, or 3 do not satisfy this property, because they are congruent to 3 mod 4. Okay, so Fermat's theorem is that if you have a prime of this form, then it is possible to find two integers, a and b, such that a squared plus b squared is equal to the prime. So it is possible to find two integers, a and b, such that a squared plus b squared is equal to p. Okay, so for instance 5 is equal to 2 squared plus 1 squared. 13 is equal to 3 squared plus 2 squared. And you can continue on, so take more primes that are congruent to 1 modulo 4. So for instance 17 is equal to 4 squared plus 1 squared, etc. And you can go on and on and on and on. Okay, so we're going to prove this in this little video. So proof. Now the proof is often detailed in I'd say second course in abstract algebra. I had it in my second course of abstract algebra, the second course of abstract algebra that I went to, which was a course entitled Groups, Rings and Modules, and it contained a proof of this result. But the first course of abstract algebra I went to was just entitled Groups, so it didn't contain nearly enough abstract algebra for you to be able to understand this proof. So I'm just going to put a few little bits of knowledge that you will need to be able to understand the proof. If you do not have these bits of knowledge, then maybe this was enough of the video for you to watch. Just learn the theorem and see that it's true by doing enough examples. Okay, so you need to know ring theory, not ridiculously advanced ring theory. You need to know the theory of quotient rings. You need to know about ring homomorphisms, obviously. What else do you need to know? You need to know about the Gaussian integers. You need to know about modular arithmetic. And the most advanced thing you need to know is that the Gaussian integers are a principal ideal domain. How do you spell that? Principal, I think. Principal ideal domain. So a PID, meaning that all ideals are principal ideals in the Gaussian integers. Okay, so if you know all of that, you should be able to follow this proof. Okay, so here goes on the proof. So what we want to be able to do is we want to be able to construct to construct. This is the construct. I'll show you the motivation for the idea behind this proof, and the person who came up with it was Gauss, the great mathematician Gauss. We want to be able to construct a ring homomorphism. A ring homomorphism that maps the Gaussian integers onto z mod pz, where p is congruent to 1 mod 4. Now, why would we want to be able to do that? So what do I mean by that firstly? So if we draw out the Gaussian integers, they are this great big lattice here, and I'm going to need some more paper. I'm just going to get some more paper. Where did I put my paper? Here we are. Okay, so here are the Gaussian integers, this big lattice. I'm not going to draw all of them. So that's the Gaussian integers here, and we want to be able to map it onto a subset of itself, which is this z mod pz. So if we say 5 is our prime, we want to be able to map all of these, so that would be 5 there, 4, 3, 2, 1, 0. We want to be able to map all of the Gaussian integers onto these 5 things, and we want it to be a ring homomorphism with respect to that. Now, why would we want to do that? Well, by the first isomorphism theorem, we know that if we can find such a ring homomorphism, so some f which maps the Gaussian integers onto z mod pz, then there exists an ideal I, which is a subset of the Gaussian integers, such that z mod I, quotiented out by the principal ideal, is the same as z mod pz. So nothing special, I'm just saying that there exists an ideal, that you know, the operation of mapping this onto this is equivalent to modding out by an ideal. Okay, and then we can say, well, we're in a PID. Well, we are in a PID, a principal ideal domain. So this ideal is principal. Ideal is principal and generated. Principal, I don't know how you spell it, whether it's an L-E or A-L. Principal, it's principal and generated by the element of smallest modulus. So when you stick a Euclidean algorithm onto the Gaussian integers, you make the size function the modulus squared. So we're just saying that it's generated, this principal ideal is going to be generated by the element of the smallest modulus. Okay, so picture, just pick whichever element is the smallest one, the one closest with the smallest modulus, and generate the ideal generated by that, and that will be equal to your ideal originally, because it's a principal ideal domain. Okay, so there exists an A plus BI such that when you generate its principal ideal, that is equal to I. Well, what does it mean then to quotient out the Gaussian integers by this principal ideal? It means the principal ideal of this is every possible Gaussian integer, A plus BI times, let's say, the Gaussian integer, we'll write C plus DI, so where C and D are elements of the integers. So this will be the great big set that you'll generate from the principal ideal. This is A plus BI, the principal ideal generated by that element. Okay, so if we have our A plus BI, let's imagine it's this element over here. It's 2 plus 2i. Then you'll have that element there. And which other elements will you have? Well, you'll have I times that, which corresponds to rotating it by 90 degrees. So you'll have, what's that, minus 2 plus 2i. You'll have the negative of it, which corresponds to rotating it by 180 degrees. So you'll have this element over here. And you'll have the one over here, which corresponds to multiplying by negative I, which is 2 minus 2i. So you'll have all of those. And then if you multiply it by other numbers, you can multiply it by all the integers. So you'll get 4 plus 4i all the way over here. So, and then that goes on, and similarly it will go down here to minus 4 minus 4i. Similarly, you can multiply it by all multiples of I and go further out that way. And then it's not too obvious that, well, maybe it is, but that you can multiply something and get the equivalent. We can sort of see it's going to form a square lattice. But for it to be, we know all ideals are going to be groups. So for it to be closed under addition, it's going to have all the elements on this square lattice, isn't it? Because if I add this to this one here, then I'll get that, and if I add all of the ones along here to all of the ones along here, I'll get this entire big square lattice. It's not totally obvious, at least not to me, that you can multiply this by something and get that. Obviously the thing that you multiply it by would be 1 plus 1i, which would rotate it, and it's kind of forming a scaled up version of this great big lattice where each point of the original Gaussian integers corresponds. You can put it in bijection with one of these, and the correspondence is given by this element here was the element that you got when you multiplied it by the original elements. The correspondence is that when you multiply each of the elements in the original Gaussian integers by your element that you're generating the ideal of, you get this other element, and that's how you put them in bijection. Okay, so it does form this great big lattice. So, then when we quotient out by this lattice, what we effectively mean is we're taking all the cosets of this. So we add on, we take an element that isn't in this. So for instance, we could take I, and then we add I to every single element of this. So we get all of these little points here, this element here, and this forms another coset of the Gaussian integers, and that forms an element of the new ring. So in a way, we could just view it as this tiny little section of elements here. Each one of these will represent an entire coset. We'll use the elements of this here as the representatives of the entire quotient ring. Of course, each of these is just representing the entire coset. So for instance, if I took I, it's the representative for all of these. So effectively, the ring is just, you can look at it just as being these elements in here, which is, because these are you have a representative of every single coset that is in your quotient ring within that little box there. So if we want to know how big the Gaussian integers quotiented out by a plus bi is, then we can count the number of elements in here, and the number of elements that is going to be in here has got to be the area of the box. It's quite difficult, in my opinion, to understand why that is, but imagine if we look, these have to pave the entire complex plane. So if you think about it, it does have to be the area of the box. But at least when I learnt this for the first time, it wasn't trivially obvious to me that the number of elements in there was the area of the box. But if you think about it, it's obvious when your principal ideal is a nice box where it's aligned with the original one. So if you have, for instance, if you generate the principal ideal, let's say of 5, just 5, you'll get this principal ideal that sort of stacks on top of here. And then if you want to count the elements, all you have to do is go along to 4. All of these correspond to this one, and obviously the ones on the boundary don't, because they correspond to the one above you, and the ones on this boundary don't either, because they correspond to that one. So everything's got this little box, and you've got 1, 2, 3, 4 to there. You've got 0 here as well, so you've got 5 times 5 elements, so there must be 25 elements in there. And because this is just basically this on a slant, that's why the area of the box, the number of elements in there has to be the area of the box. But the area of the box is just the length of this times the length of this, and the length of this is the square root of a squared plus b squared, where a plus bi is our complex number here. So if we square that, it's equal to a squared plus b squared. So that is our the size of our quotient ring. But we know that this ring here, down here, was isomorphic to z mod pz. So the size of it was equal to p modulo 4. And I'm going to show you why we can only do it when it's p modulo 4. So if I can find that ring homomorphism, then everything follows from that. It follows that there is two integers a and b such that they are equal to p. Okay, so all I need to now do is construct this ring homomorphism. So, construction of the ring homomorphism. Construction of the ring homomorphism. The ring homomorphism. Okay, so firstly I'm going to show you why it has to be modulo 4. Why p has to be congruent to 1 mod 4. The reason is that if it's not, there is no possible element that you can possibly hope to send I to. You see, when you do a ring homomorphism, let's think about the abstract ring homomorphism. So let f be a ring homomorphism from the Gaussian integers into, since we're doing it, z mod pz. We know that phi of a times b must equal phi of a times phi of b, because it's a ring homomorphism. We also know that phi of 1, that this implies that phi of 1 is equal to 1 in this new ring. We also know that phi of inverses, additive inverses in this case, must go to the additive inverse of the element that the original element goes to. So the fact that these properties hold tell us that phi of minus 1 must go to minus 1 in the ring, because 1 goes to itself. And therefore, we know that phi of I composed with I is equal to, by this property up here, it's phi of I times phi of I, but it's also equal to phi of minus 1, we know. So it must be equal to minus 1. Therefore, whatever I is mapped onto, it must compose with itself to make minus 1. I'm going to show you that unless p is congruent to 1 mod 4, there is no element in here that that composes to give 1. Well, yes, that's true. If p is congruent to 3 mod 4, then it's not. Then unfortunately, there will be no element such that this happens. And the reason is this. Look, if p, and firstly, let's just do a bit in. I just need to say something prior. If p is a prime, it is odd. It is odd or 2. We're not interested in 2. So p is either congruent to 1 mod 4 or it's congruent to 3 mod 4. Those are the only two cases. If it's congruent to 2 or 0, then it's even. And there's only one prime that's even. So all other primes are either congruent to 1 mod 4 or they're congruent to 3 mod 4. Now, if it's congruent to 3 mod 4, then consider z mod pz. What is the size of the... Firstly, we know that z mod pz is a field, so what is the size of the unitary group? What is the order of this group? Well, it's p minus 1, because you just have to take out 0. All other elements are invertible. P minus 1 is therefore... it's some multiple of 4 plus 2. So we could factor out 2, but it would be 2 times an odd number. Understand that, because we've only got 1 2 here, and it is some multiple of 4 plus 2. We can factor out 2 here and get another 2 here, but we'll get 1. So we'll get 2n plus 1. 2 times 2n plus 1, and 2n plus 1, 2 times n is all where n was an integer. In fact, it was more than an integer; it was a natural number. Could it have been 0? It could have been 0 or 0. A joint union the set containing 0. Okay, so the 2n is an even number plus 1. It must be an odd number, so it's 2 times an odd number. If we had an element in z mod pz that multiplied with itself to give minus 1, then such an element, let's call it a, to the power of 4 would equal 1, because a squared is equal to minus 1, a to the 4 is therefore equal to 1, because minus 1 times minus 1 is 1. Okay, so I don't want to change term paper because everything's on here. That would now we apply Lagrange's theorem. Lagrange's theorem tells us that the order of an element must divide the order of the group. This element has order 4. Will that divide 2 times an odd number? Absolutely not. So you cannot have an element of order 4 in this group. Therefore, an element of order 4 multiplicatively cannot have been in this ring if P was not congruent to 1 mod 4, if P was congruent to 3 mod 4, and therefore we don't have a hope of being able to produce such a ring homomorphism for that ring. Okay, so let me show you for P congruent to 1 mod 4. Okay, so the first thing to say is that we need to know something called, well, firstly, what is minus 1 in Z mod PZ? Well, I hope you know this, that it's P minus 1, because if I add 1 onto P minus 1, I get P, which is 0, so therefore P minus 1 must be equal to negative 1 in our ring mod P. Okay, and now we need to know something called Wilson's theorem. Wilson's theorem basically states that if we work in Z mod PZ, and we take 1 times 2 times 3 times 4 times all the way up to times P minus 1, then that must be equal to minus 1 mod 4, mod P rather, mod P. The reason being that P is a field, so the only element of this ring that you're not multiplying is 0, because then everything goes trivial if you add that on. So all the elements are invertible here. All of these elements are invertible. Now, one element has its inverse as it being is for one element. In fact, for 2 elements, its inverse is itself. Well, 1 you can argue has no inverse in a way because it is the identity. So we'll just ignore 1. But P minus 1 is the only element that has its inverse, for which its inverse is itself. Therefore, all the other elements have their inverses in this multiplication. So by commutativity of this ring, you can swap them around and associate as you will, and you'll get each of them cancelling with their inverses and going to 1. So all of this will go to 1, basically. All of this, you've got 1, the identity, times all of this stuff that's multiplied by its inverse somewhere, times P minus 1, and P minus 1 was minus 1. So that's the proof of Wilson's theorem. Now, the other clever thing is that if P is congruent to 1 mod 4, that means that P minus 1 is a multiple of 4, is some n4. 4n rather than n4. N is an element of the natural numbers. Could it be 0? Well, it could, but it would make it a bit trivial. In fact, could it? I don't know if the I think the 0 ring does count as a field, so it could, but we're not interested in that. N is an element of the natural numbers. Okay, so I can write 1 times 2 times 3 times 4, and I can split this in 2. It means that P minus 1 is an even number, so I can go all the way up to P minus 1 over 2. That is an element in this ring. If this was an odd number, we'd have problems doing that, but this is an even number, so there is such an element that's halfway along. Plus P plus 1 over 2, all the way up to P minus 1 over here. And that's congruent to negative 1 mod P. But if you notice, this is the additive inverse of this. This is the additive inverse of this. All of the ones in the middle, so if we have P minus 2 here, will be the additive inverses of them, because 2 plus P minus 2 is 0, because it's a multiple of P. P minus 1 plus P plus 1 over 2 makes P, so it's 0 as well. So all of these are additive inverses, so we could replace all of this with the negatives of all of these ones. So we could write negative P over 1 minus 1 over 2 all the way up to times P minus 2 times p minus 1. Oh, sorry, what am I doing? Times the negative 2 times negative 1. Then what we can do is factorize out minus 1, however many times it is. So we need to know how many times we've got minus 1 multiplied in here. Well, that's the number of elements we have here. And how many elements do we have here? An even number, because it was p prime, it was the number we had was 4m. We've already split it in half once, but we can split it in half again. So, well, we've got an even number here. So it's minus 1 times an even number, which is 1. Which means that this must be equal to this. So we've multiplied two things that are exactly the same by one another to get minus 1. By Wilson's theorem, this was equal to minus 1. Therefore, if we take this number here, 1 times 2 times 3 times times p minus 1 over 2, it means that that element had all multiplied by itself squared was equal to minus 1, and therefore it had order 4. So call this element, what should we call it? Element E, and that's the element we're going to map I onto. So here I'm going to show you the construction of our ring homomorphism. So ring homomorphism then. Homomorphism. So let's draw a picture and show you the ring homomorphism. So the idea basically is, if you're an integer, then what I'm going to do with you, f will map you, if you're an element of just the integers, so this line here, f will map you onto z mod pz. Okay, so that's our first map, so that tells me where to put all the integers, okay? And we know that this is a ring homomorphism. Now, I'm going to, in my bigger map, this is our small map, so I'm going to call big F. F is going to map F is going to map specific. It's going to map the element I. So f of I is going to be this element E. So it's somewhere. So if this is, let's say this is how many have I got here? Oh dear, I can't make it wrong. So we'll have to go up to 13 now. Damn it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this is my ring here now, so this is 13, so it would be all of these elements up to here, stopping at 12, and somewhere in here would be this element E. We don't know where it is. I can tell you how to construct it in the case of 13. All you have to do is multiply 1 by 2 times 3 times all the way up to p minus 1, which is 12, over 2, which is 6, so 4 times 5 times 6, and you need to do that in z mod 13. So of course, z mod 13z we'll call it. So you have to do this modulo 13. Oh dear, you can't see this. Right, so what I was saying is that if you want to find which element E is for 13, all you'd have to do is multiply all of these together, modulo 13. So what you'd basically do is you stick this into your calculator, do it in the integers, and then you go up and find what you'd use the Euclidean algorithm, find the smallest number which is a multiple of 13 that's lower than your number, and then take the remainder. And that would be your answer, and that would be your E in z mod 13z. Okay, and now because if we've got any hope of, because we want big F to be a ring homomorphism, if there's any hope at all of it being a ring homomorphism, then F must map C plus DI onto, because we can split it up, because it's a ring homomorphism, we can split it up into that, and because it's this ring homomorphism, we can split it up further into F of D, F of I. Now, C and D are integers. I know where the integers go. I know where I goes. So you map this onto little f of C plus little f of D times element E. So that's, we claim, a ring homomorphism. I now need to prove to you that that's a ring homomorphism, and then I'm done. Okay. So, onwards we go. Right. So, I need to show you two things. I need to show you that f of, let's say, two arbitrary Gaussian integers, a plus bi plus c plus di, is equal to f of a plus bi plus f of ci. So that's the claim. Okay, so what do I know this is equal to? Well, I can rewrite this as f of a plus c plus b plus di. And then I can write that as little f of a plus c plus little f of b plus d times e. And because little f, remember this mapping from z to z mod pz is a ring homomorphism with respect to the integers, a and c are both integers, I can rewrite this as little f of a plus little f of c plus little f of b e plus little f of de. Okay, and then I can regroup little f of a plus little f of b e plus little f of c plus little f of d e, and then I can just write that as that is big F of a plus b I, and this is big F of c plus di. Done. Quaderat demonstrandum for that one. Now I need to show you the slightly less trivial one, a plus bi times c plus di is equal to, I can multiply this out, ac minus bd plus bc plus ad I, and that goes to little f of ac minus bd plus little f of bc plus ad times e is equal to, because little f is a ring homomorphism, I can write this as f of a, f of c minus f of b, f of d plus little f of b, little f of c times e plus little f of a, little f of d, e. Now that looks like a total mess, but we know what the answer is going to be firstly, so we have a big suspicion of what we're going to be able to do here. We suspect that it's going to be f of a plus f of b times e times f of c plus f of d e, and admittedly if you just had to try and spot that that was equal to that, you'd struggle, but we know where we're heading with this proof, so we can kind of see that it's going to go to there. So all I need to now check is that this really is equal to this. So f of a times f of c, I get this here. F of b times f of c times e, I get this thing over here. F of a times f of d times e, I get this thing here. And these two, this is the only term where I've fooled you, I've conned you. F of b times f of d gives you this. E squared, what? We've got a minus 1. But e was this number. We're working in our new field, in our new ring, remember, z mod pz. E was this number which did square to give minus 1 in the new ring. So this is correct. Fantastic. So I can just write that as big F of a plus bi times big F of c plus di. And there we are done. There is the proof that this function that I constructed in this so sort of like odd way, I just sort of found the element that I just sent all the integers onto z mod pz. That made sense. But then I just found the only element I could possibly hope to go on to, and then I just constructed it by the fact that it had to be a ring homomorphism, and somehow I got lucky enough that it was a ring homomorphism in reality. And that is how Gauss proved Fermat's theorem. Of course, he had the knowledge that Fermat's theorem was probably true. I mean, if you try enough examples, it works and it works and it works and it works. So he had the belief that it worked, and that probably sort of drove him to think that, okay, surely this ring homomorphism does have to work, therefore. But it was an utterly ingenious thing, and he did all of this prior to, you know, the lingo of ring theory had been invented. So, yes, Gauss was one of the greatest mathematicians ever to have lived. Fermat, we don't know what Fermat's proof of this theorem is. Most people know that Pierre du Fermat made a huge number of theorems, a lot of which have turned out to be very, very true. Some of which, you know, the last one was only proven about 30, maybe 40 now years ago, and required the most horrendous abstract algebra. But as I say, he did not leave a proof of this, so we do not know what Fermat's original proof of this was, but we do believe he probably did have something up his sleeve.